What Earl's here?
Tahoka's here.
Wellman's here.
All right, good morning, everybody. It is time to begin the class. Okay, so any questions over the homework? Okay, my monitors just went blank. Is everybody still there?
Tahoka's still here.
Toga's still here? Wellman?
Wellman's still here.
And Woodharrell?
Yes, sir.
And can you see me, or the sign?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. Then I will assume that the problem's on my monitor, not with our connection. So, okay, there are some computer problems with the computer in this room, so I still can't access my math lab from this computer. But if you have questions, please ask them. You're just going to have to tell me what the question is, not just what number it is. So do we have any questions over the homework, operations and stuff on vectors? We're all good? Okay. Then what we will cover today is using those vectors in applications. We just have a few examples, but they are fairly detailed, and we will need to make sure that we understand everything that is going on here. So you'll recall we said that a vector has a magnitude and a direction associated with it. And one of the things, if you've talked about it yet in your science classes, that a vector is especially good at talking about is forces. So that's going to be our first application. Is forces. Now, we have two kinds of forces that we're going to look for, and both of them revolve around a word called equilibrant or resultant. I think this might depend on the age of the books. I grew up with resultant. This book uses equilibrant, and I think a lot of newer books use equilibrant. In any event, it relies on Newton's laws. Specifically, if I'm not mistaken, it's the second law that says the resulting force on an object is the sum of all acting forces. So, for example, let's say we've got an object here that we're pulling on, and you and your buddy go and you pull on this, but one of you is pulling this way, and the other one is pulling in a slightly different direction. Well, we can see, if you remember from the previous section, we can break any vector down into a vertical component and a horizontal component. And we're going to do the same. So if we do this for each of these, we can kind of see what's going to happen here. The things moving up and down here in this direction aren't really going to do anything. They might cancel each other out even. But these horizontal directions this way, the guys going, both forces are going to the right. And we can see, according to our parallelogram law, that we have this force as a result. So this is going to be force 1, this will be force 2, and this guy right here is going to be the resultant. Okay, so let's do an example that uses this. How do we calculate the resultant? And then we'll move on to the next example. Okay, so we have two forces, one of 54 newtons, one of 42 newtons, and they are acting on a mass A. The angle between the forces is 98 degrees. What we want to find your book uses equilibrium. I should probably use that word as well. Find the equilibrium and the angle it makes with the 42 Newton force. So what does that mean? What is the picture? Remember, pictures are really important. What is that picture associated with this? Well, we're going to create a mass A, and then we have two forces acting at a 98-degree angle. So we've got that guy there. And we've got that guy there. Here are our forces. And we'll call this one the 42 Newton force and this one the 54 Newton force. It doesn't particularly matter. We just need to make sure everything's labeled. Okay. Now, what does that mean we want? Well, according to our parallelogram rule, that's parallelogram-ish. That red line is our resultant, and the equilibrium will move in the other direction. And the thing to remember here is that the magnitudes are the same. The magnitudes will be the same. Okay, we also have, right, we forgot to write down, this right here is 98 degrees. So what do we need to find? We need to find the equilibrium, which is just the opposite direction of the resultant. And we'll call this guy alpha. We need to find that angle right there. Find the equilibrium, that's him, and the angle it makes with the 42 Newton force, that's this right here. What other information can we get that's not in the problem already? That is right here. if we recall from geometry, in a parallelogram, opposite angles are congruent. So that means if this is 98 degrees, then that's 98 degrees. Adjacent angles are supplementary. So this is 98, that means this is 98. But if this is 98, that means this measure here is going to be how many degrees?
82.
Right? 82 plus 98 is 180. And now, what can I use to find this length? I have a side. I have another side, right? This is still a 54 as well. So I have a side, and I have the angle between them. What will give me this right here?
The law of cosines.
Law of cosines, right? We have side, angle, side, right? 42, 82 degrees, 42 newtons, and 54 newtons. So use law of cosines. And law of cosines will give us this resultant. So fill out the law of cosines, and I will ask one of you for the equation that we're going to solve. I'm going to switch sheets. I'm going to redraw this in the meantime so that we still have it to reference. Okay. So what is the law of cosines going to look like to find this force? We'll call it F. It's a vector. Somebody from Whit Herald, go ahead and give me, I don't want the answer. Well, we can calculate that. I just want the equation. Like the use of the law of cosines.
C squared is equal to 42 squared plus 54 squared minus 2 times 42 times 54 times the cosine of 82.
Excellent work. That is exactly right. The magnitude of the force is going to be this application of the law of cosines. And then we punchy into the calculator and get our magic number. And we'll go ahead, looks like we'll just round to the nearest integer here. Forgot that squared. So the square, make sure this jives with what you have. There's what I get for the magnitude squared. So the magnitude of the force by itself. And like I said, we're going to round to the nearest integer here. So 64 newtons. Does that jive with everybody else?
Yes, sir.
Yes, sir.
Excellent. Now, the other thing we need, right, so this is the first part. This is the magnitude of the resultant and the equilibrant. What was the other thing we were asked for? The other thing we were asked for is alpha here. But to get alpha, I need to know this angle right there, and we only know the full thing as 98 degrees. There's going to be a temptation here, and that temptation is, oh, well, let me just take the 98 degrees and we'll just cut that in half. And that'll be the angle we want, but that's not necessarily true. The reason it's not necessarily true is that the diagonal of a parallelogram is not necessarily an angle bisector. That's an important note. We will write it here. The diagonal of a parallelogram is not necessarily an angle bisector. It is if you have a square. If your parallelogram is a square, then it's totally an angle bisector. But as we can see, this is not a square, so we don't have an angle bisector. So what rules can we use to find this angle, given that we have now 3 sides and 1 angle? What can we use to find
law of sines.
all at once? That's excellent. We can use the law of sines, yes. So this guy right here, we'll call him theta. We're going to find theta with the law of sines. So I have, remember we need a combo. I've got 64 and 82 degrees as a combo. And I need this angle, which means I'm going to use the 54 as my other side, right? We always need opposite sides. So we take our combo and we set it equal to the thing that we don't have. And we solve for theta. So theta will be the arc sine of 54 times the sine of 82 over 64. And what do we get?
56.67.
That is correct. Right, and we'll go ahead and round that, because we're just in a rounding mood today. We'll round that to 57 degrees. So, what does alpha have to be? Right?
123 degrees.
Very good. Here's the theta that we just found, 56, and alpha is the supplement. So 180 minus 57 is 123 degrees. So there is our new forces situation. We found F using the law of cosines. We found theta using the law of sines. Took the supplement to get the angle that was requested of us. The two things that I want to stress here, because they're not being made clear in your textbook, right? Because there's an example just like this, but with different numbers. But the things that it doesn't talk about, I think, are the things that are really important that we tend to forget in these problems. And they're all of those geometry principles that you haven't seen for probably 2 years. The first one is how parallelograms work with their angles. Opposite angles are congruent, and adjacent angles are supplementary. So when you have this situation and you draw your resultant in here, if you want to find that angle, it's the supplement to the angle between these two forces. So that's an important factor right here that we need to recall from geometry. Everything else, law of cosines to get the resultant and everything else, that was stuff we did this semester. That's stuff we did this week. But this you might not have remembered. And then the other thing, what the diagonal of a parallelogram does, this is, I would try to burn this into your brain right here. This is a very, very common mistake when students are doing these kinds of problems, that, oh, well, this looks like it's bisecting the angle, so I'll just cut it in half. But that's not true. We can see it right here. 57 is not half of 98. This is bigger than half of 98. And we need to have that knowledge. So make a note of this, especially when you're doing the homework problems that involve finding equilibriants and resultants. That's going to save you a lot of heartache when you're doing all this work and you don't get the right answer. Okay. Any questions here over this problem? Something that I went too fast on, or that you just need re-explained? Okay, we will move on to the next example. And the next example is one of my favorites. We've got a box on a ramp, and let's say that ramp has a 12-degree incline. And we will say that the box weighs 50 pounds. Now we all know how gravity is going to work here. This 50-pound box is going to slide down the ramp unless we have something to prop it where it is. So the question is, what force is required to keep the box stationary? What force is required to keep the box stationary? Well, let's look at the forces. Gravity is not going down the ramp. This is the first thing you want to pay attention to. Gravity doesn't go down the ramp. Gravity goes straight down. So we're not having to support the entirety of the box. All we need to support is the component that's going to go along the ramp. Right? Does that make sense? There's going to be that component that goes up and down the ramp. This is the force I need to apply. So we'll make a version down here and a version down here, and they'll meet at right angles. And now I will color in red the vector that we need to find, this guy right here. They are parallel, and they are the same magnitude, so where we put that vector doesn't make any difference. In order to make the triangle, I start with this vector, and then to make the triangle, I drop the vector down here. So we need to know this angle, and we will call it theta. And I'm going to make an assertion here. And I want you to go and justify this at home. And my assertion is that theta is exactly equal to the incline of the plane, the incline of the ramp. And, in fact, this is always the case. It doesn't matter how big the ramp is, it doesn't matter how heavy the box is, this angle here and this angle here are always the same. These two angles are always the same. So, what are our forces? I've got a 50-pound force going straight down, and I need to find this guy right here. Well, I've got a right triangle, I've got an angle, so how do I find this force? Think back to chapter 2.
The sine of 12?
The sine of 12, right? I've got a hypotenuse here of 50, and I've got this angle which we said was 12, and this guy right here is going to be 50 sine of 12. So the magnitude of our force is 50 times the sine of 12 degrees, and what's that?
$10.4.
10.4. And we're still in a rounding mood. Let's go ahead and say 10. Right, so we didn't need all 50 pounds of force to hold that box in place. I didn't need all 50 pounds pushing this. I just need 10 pounds pushing this. Does that make sense? Good, bad?
Doug's good.
Okay.
It's good.
So now, let's turn this on its head, because this is another thing that we do sometimes, at least in a physics class. We're going to take the same situation and we still have a box. It doesn't have to be a box. It can be a car or a wagon or whatever. But I like using boxes because that's what my physics teacher used, and I've just developed a 20-year habit. So, let's take this box that weighs 74 pounds. And what we know is that it requires...
Mr. Grills, will you scoot your paper up a little?
Sorry. There you are. Actually, we need a little higher anyway, so there we go.
Thank you.
No problem. Now, instead of knowing about the ramp, what we know is that it requires 18 pounds to keep this box from moving. What we want to find is the angle theta. That's what we want to find. So how are we going to set this up? Well, the picture-wise, I'll bring this down again for a second. This is the same situation, right? So I'm going to start this in this kind of situation, and because of that, we get the same assertion right here. That whatever angle I need here is going to be identical to the angle that I get here. These angles are going to be the same. Make that easier to see. So, what does that tell us? If this force is 18 pounds, that means that force is 18 pounds. And how do we find theta?
The arc sine of 18 over 74.
Right? Sine is opposite over hypotenuse, and that's exactly what we've got. We've got the opposite and the hypotenuse. So theta will be the arc sine of 18 over 74, and I assume that you already had that calculated?
14.078.
14.078 degrees. We'll go ahead and go for 14.1. And if you leave 3 decimal places, no one's going to fault you. Just a second. There we go. If you leave 3 decimal places, I'm sure that'll be fine. For my math lab, pay attention to what it tells you to do. If it says round to the integer, round to the integer. Otherwise, it's going to mark this wrong, and you'll get mad, and my math lab won't care, and it's a lot of wasted effort. So just make sure you read that blue text. So, using the same kinds of things with vectors that we talked about before, only instead of using law of sines and law of cosines, I have right angles involved, so I can use right triangles to talk about these two problems. So we have that theta equals 14.1 degrees. That's the incline of the ramp that allows this to happen. Two force problems, 2 different plans of attack. How do you know which one is which? Look for keywords. Look for draw pictures. You will, in these kinds of problems, you will always see the word incline. Or ramp. That's how you're going to know you have this kind of a problem. Another key is you want to keep something stationary here. That's going to be, this is always the given, but you'll also see words saying, how do I keep this from moving? Or it takes this amount to keep it stationary. Or I want to hold it up. Right? Those kinds of words to make you believe not falling, not moving. Those are going to be how you identify these problems. Those parallelogram problems from before, right, these guys, you're always going to see the word equilibrant or resultant, and you're always going to have two forces acting at the same time. That's how you identify parallelogram problems. You have two forces acting at the same time. You'll always see the words equilibrant or resultant. Those are going to tell you what kind of picture to draw, and as we've already discussed at length so far, the pictures are going to be incredibly important. In fact, the only time the pictures will not be important is never. We'll talk about some stuff that you don't use pictures on in the first place, but everything else, if you can draw a picture, it's going to be essential to these problems. If you haven't taken a physics class yet, this will be given in stark relief when you take a physics class, if that's in the cards for you, if that's part of your life plan, etc. Okay, so yeah, we've got the parallelogram problem, we've got these two incline problems. Are there any questions here, something you need gone over again, or that you're just not comfortable with? We're good?
Toke is good.
Okay.
Wellman's good.
Excellent. Okay, so the next kind of problem, and I'm sure you knew this was coming. Bearing. Our old friend bearing. That is what we are going to talk about now. So let's say, now the reason that this is a good time to start this is now we have law of sines, now we have law of cosines. Before, in chapter 2, every step we had to take was predicated on the fact that our bearings made right triangles. So before, step 1 is confirming right triangles. Quick note about confirming right triangles. You recall there were some bearing problems on the first exam. Nobody but two people took the steps to confirm that they formed a right triangle. I let it go. So everybody, if you got the right answer on those problems, you still got full credit. If you used the right trigonometric identities and functions, you still got full credit. That will not fly on the final exam. On the final exam, if you have a bearing problem and you use right triangle stuff, you need to confirm that your bearings form right triangles. If you do not do it, you will lose credit. That part is a very important part, and part of the reason is because of what we're going to see now. So I let it slide before, but I will not let it slide on subsequent exams, especially not the final exam. So please make a note of that, keep it in mind, always confirm what kind of triangle you have before you start messing with solving it. So before, step 1 was confirming right triangles. Now we're just going to determine what kind of triangle we have. Because we could be using a right triangle, or it could be something that we use law of sines, or it could be something where we use law of cosines, but we're not going to know until we draw a picture. So in case I'm not emphasizing this enough, draw pictures. If you have picture issues, email me your pictures. I can look at your pictures, determine if it accurately describes the problem. If it doesn't, I can show you where the issues are and how you should make your pictures look. If you watch the videos, if you're watching the videos on YouTube, you'll hear me talk about how we're making the pictures every time. And if that's not enough or not good enough, again, you send me an email, I can walk you through the process.
I got this not working.
Everything okay there with Harold?
Yes, sir.
Okay, just making sure.
I didn't know the things were on.
They're always on us.
He said it wasn't. He said his things weren't working.
I think one of you still has a microphone on. There we go. Okay, so let's take an example. And we have a ship leaves port. At bearing 25 degrees, 25.0 degrees, so I think we'll be rounding to 1 decimal here. And travels 61.4 kilometers. Then turns due east. And travels 84.6 kilometers. And we have two questions. How far is the ship from port? Question number 2, what is its bearing? Okay, so pictures. Our bearing was given in raw degrees, which means we're always going to be we're always going to be clockwise from north. So what we'll do is we're going to plot our port right here. Let's scroll this up. And we draw a line going in the north direction. And then what do we have? We have a 25-degree bearing. So there's our 25-degree bearing. And we're going how far? 61.4. And then we turn exactly due east. So which way is due east? That's right here. And we did that for 84.6 kilometers. And what we want is this. What we want is this. So this is the distance from port, and I want that angle right there in red as well. So let's zoom in on the picture, make that a little clearer to see. We want this length, and we want this angle. So the reason the picture is so important, let's put another north-south line here, is because it's going to tell me what all my angles are. This is a north-south line, and then I'm going straight east from here. So that's a right angle, right? What is this angle? Can somebody tell me what that angle is?
25.
Why is it 25?
It's an alternate interior of the parallel lines.
Very good. Is it an alternate, right? I have parallel lines. North is always parallel to north. And I have alternate interior angles. So that's going to be 25 degrees. So what is the angle measure of the entire angle?
degrees.
115 degrees. Okay, so now look at the triangle very carefully. What are we going to use to find our new bearing?
Law of sines.
Why law of sines?
You have the angle 61.4 with the opposite side of 84.6, and you can use your angle 115 to find your bearing, or your new line.
Okay, so this is not an angle, right? This is this is the distance there.
Yeah, never mind.
So which one is it?
Law of cosines.
Law of cosines, right? I have a side, an angle, and a side. Generally speaking, if you have a triangle and you're not sure what congruence rules to use, write them down. So like if I had side-side angle, then that means I have a side, and I should have this angle right here. Or if I have angle, angle, side, then I should have an angle, and a side. And we can identify which ones are which. So if you can, if it helps, and it might, see if you can make this identification before you declare law of sines or law of cosines. And it might save a little bit of having to rework the problem because of conflicting information. Okay, so let's work the law of cosines. This is going to be a vector D. So the magnitude of D squared, side, will be 61.4 squared plus 84.6 squared minus 2 times 61.4 times 84.6 times, darn it, I ran out of room, cosine of 115 degrees. And we go ahead and punch that out. What do we get? What is the square of the magnitude?
After we got the square root, we got 123.8.
That'll work. The square, 15,317.65. So the magnitude of the vector will be 123.76, which we can round to the nearest tenth. That'll be 123.8 kilometers. How are we going to find the bearing?
You could use law of sines to find the angle of the triangle and add it to 25 degrees.
Very good. Right, we've got an angle here, we'll call it phi. So I have law of sines to find phi, and then we'll add it to 25 degrees. So we have that phi, right, where's our combo? Our combo is D, the vector D, and the 115 degrees. And then which side are we going to use to find phi? The 84.6 or the 61.4?
The 84.6.
Thanks a lot.
Right, the 84.6, that's exactly right. So, we'll have the arc sine of 84.6 times the sine of 115 all over 123.8. And we go punch, punch. And I get 38.3 degrees. So the bearing is 38.3 plus 25, which is 65.3 degrees.
Mr. Groves, are we still having the test on Friday? And will we have a review up?
The review should go up this afternoon, and we are still slated for the exam on Friday, yes. So I will send out an email reminding you all of what I just said because it cut me off literally mid-sentence. I apologize. One day I will get better at this timing thing when it comes to announcements at the end of class. So all that said, have a great day, everybody. I will see you on Friday for the exam. Again, that review will post, and I will take care of all that this afternoon. All right. Have a great day, everybody, and I will see you on Friday.